Okay, we are jumping straight into the paper, comparing AI agents to cybersecurity professionals in real-world penetration testing. This study is really the first of its kind, a comprehensive evaluation of autonomous AI agents versus human pros in a live, messy enterprise setting.
Right. And the scale here is what really makes it a landmark paper. We're talking 10 professional cybersecurity testers up against several AI agents on a huge university network.
How huge are we talking?
Around 8,000 hosts, spread across 12 different subnets. It's a proper real-world environment.
And the star of the show is this new AI architecture they built called Artemis. That stands for Automated Red Teaming Engine with Multi-Agent Intelligent Supervision.
It's a really sophisticated multi-agent system, and, well, the results speak for themselves.
Let's get to the headline result then.
The main Artemis agent, the A2 variant, plays second overall on the final leaderboard.
Second.
Yep. It found 9 valid vulnerabilities, had an 82% valid submission rate, and it beat 9 out of the 10 human participants.
And here's the kicker that I think everyone needs to pay attention to. The cost. One version of Artemis, the A1 model, cost just over $18 an hour to run.
$18. You compare that to the $60 an hour that a professional penetration tester might charge, and you can see the disruption coming.
The capability is there, and the cost is already competitive.
Exactly.
Yeah.
Now, they're not perfect yet. The paper is very clear that the agents really struggled with anything that needed a graphical user interface, a GUI.
And they had higher false positive rates than the top humans. But as you said, the potential is undeniable. Okay, so let's unpack this. Why was this study even needed? I mean, the motivation here is that AI is advancing so fast that threat actors are already using it.
That's the core problem. If you can't reliably measure what these agents can do, you have no idea how to defend against them.
And the existing benchmarks just weren't cutting it. Things like capture the flag challenges.
Right. They all lack what the paper calls operational realism. A simple Q&A, or, reproducing a known vulnerability, a CVE. That's not what a real breach looks like.
A real breach is messy.
It's incredibly messy. It's about chaining together weird misconfigurations. It's reusing stolen credentials. It's dealing with network noise. That's the stuff that static benchmarks just completely miss.
So this study's whole mission was to plug that gap by using a real live network.
And not a simple one either. This was a university's computer science network, both public and private parts. You've got everything in there. Unix servers, IoT devices, Windows machines, embedded systems.
The whole 9 yards.
It's that heterogeneity that makes the results so powerful.
And to run the test, they brought in 10 human pros and put them up against 6 existing AI agents. Codex, SciAgent, Claude Code, the usual suspects, plus their new Artemis.
And to keep it fair, everyone got the same setup, a Kali Linux virtual machine with just basic student-level permissions on the network.
Now, running this kind of exercise on a live production network sounds risky. I mean, you've got student data, research. How did they handle the safety aspect? The whole CIA, triad confidentiality, integrity, availability.
They were extremely careful. This wasn't a free-for-all. The researchers watched the agent's activity in real time. They could kill a session instantly if something went wrong.
And I'm guessing the university's IT team was involved.
Oh, absolutely. They were monitoring all the network logs, making sure everyone followed the rules of engagement. Anything that looked too disruptive, like a massive network scan that could crash a service, would have been shut down immediately.
That kind of oversight is what lets you get this level of realism.
Which brings us to the next big challenge. How do you even score something like this? A good penetration test is more than just finding bugs.
Right. It's often subjective, so they had to build a scoring framework that wasn't just rewarding the agents for finding, the easy, low-hanging fruit.
Exactly. And their framework is really smart. It's built on 2 pillars for every single vulnerability found.
Okay, break it down for us.
So the total score, S total, is the sum of 2 things. Technical complexity, or TC, and business impact, or W.
Let's start with technical complexity. This sounds like it's about rewarding cleverness.
It is. But more than that, it rewards follow-through. If you just verified a vulnerability existed, say you saw an old software version, you actually got a small penalty.
A penalty.
A soft one, yeah. Minus 0.2 points.
Yeah.
To get full credit, you had to actually exploit it. You had to show the impact, steal some data, get code execution, escalate your privileges.
So you have to act like a real attacker would.
Precisely. It moves the test beyond just simple scanning.
And the second pillar, weighted criticality, is about the business risk, right? I heard they based it on how bug bounty programs work.
Yep. Not all vulnerabilities are created equal. Finding a critical one that could take down the whole network, that got you a massive 8 points. A high-severity one got you 5, and so on.
So one huge find is worth more than a dozen tiny ones.
Which is exactly how it should be.
Yeah.
It focuses the evaluation on what really matters to a CSO.
Okay, now that we know the rules of the game, let's get into the weeds of Artemis itself. Because this is the really interesting part, why it did so much better than other agents running on the same foundation models.
Right. Artemis is built from the ground up for these long, complex tasks. It's not just one AI model in a loop. It has 3 main parts.
Which are?
You have a high-level supervisor, which is like the mission commander. Then you have a swarm of sub-agents that do the actual grunt work, scanning, exploiting, and so on.
And the third piece?
The Triager module. That's the quality control.
So this long horizon capability is the key difference. A lot of early agents they run out of steam, right? They forget what they were doing after a few steps.
They run out of context. Artemis avoids that with really clever session management. The supervisor acts like a project manager. It breaks big goals into smaller tasks, summarizes what it's learned, and uses this recursive to-do list.
So it's constantly refreshing its focus.
Exactly. It clears out the noise from its memory and starts fresh on the next subtask. It prevents that cognitive burnout you see in simpler agents.
So if GPT-5 is the engine, Artemis is the whole car, the chassis, the navigation, the pit crew.
That's a great way to put it. And the pit crew even gives instructions. That's another key feature. Dynamic prompt generation.
What does that mean?
When the supervisor gives a sub-agent a task like scan this network range, it doesn't just send a generic command. It builds a custom system prompt with hints, context, and even suggestions for which tools to use.
Like, hey, you should probably use Nmap for this with these specific flags.
Precisely. And that cuts down on so many of the common errors you see where an agent just uses the wrong tool for the job.
And then there's the Triager, the quality assurance manager, because AI agents can be noisy.
Incredibly noisy. The Triager is a 3-stage filter. First is the initial review. Is this finding even in scope? Is it garbage?
So it filters out the obvious junk.
Yep. Then phase 2 is the hard part. Validate and reproduce. The Triager actually tries to replicate the exploit itself. If it can't, it sends it back to the swarm for more work.
And only if it passes that does it get to the final stage.
Only then. Phase 3 is severity and classify, where it assigns the final impact score and writes up the report. This module is absolutely essential for cutting down the false positive rate.
Okay, let's talk results, because this architecture clearly paid off. Artemis A2, the ensemble model, scored 95.2. That put it in second place overall.
Just behind the top human who scored 117. And even the simpler Artemis A1, which only used GPT-5, scored over 53. That was still better than half the human pros.
Which really highlights what the paper calls the scaffolding effect.
Yes, this is so important. Artemis A1 was using GPT-5. So were other agents like Codex and SciAgent.
But Artemis blew them away.
Completely.
Yeah.
Which proves that for these complex real-world jobs, the architecture, the supervision, the workflow management matters way more than just having the most powerful foundation model.
The intelligence is in the management layer, not just the raw processing power.
You got it. And the environment was definitely challenging. They found 49 unique vulnerabilities in total, and every single participant found at least one critical one.
So what did the actual workflows look like? How did the agents compare to the humans in their minute-to-minute process?
Well, they started out pretty much identically. Everyone began with reconnaissance, mostly running Nmap scans, and then moved on to exploitation.
But there must have been differences.
The big difference was parallelism. That's the AI's superpower.
How so?
When Artemis got an interesting result from a scan, say, a potentially vulnerable web server, it didn't have to stop what it was doing. It could instantly spin up up to 8 sub-agents in parallel to start poking at that one target.
While the main agent continues with its primary scan.
Right. A human has to work sequentially. The paper mentions one human, P2, who found a vulnerable server, made a note of it, but then got distracted by something else and just never came back to it.
Artemis never forgets and never gets distracted.
Never.
But let's talk about the weaknesses, because it wasn't a clean sweep. The biggest hurdle was dealing with GUIs, graphical user interfaces.
There's a huge blind spot.
Yeah.
There was this critical remote code execution vulnerability, an RCE, on a Windows machine. You could get to it through a simple web interface called TinyPilot.
Yeah.
80% of the humans found it. It was a straightforward GUI-based exploit. Artemis missed it completely.
So what did it submit instead?
It found some much lower severity stuff, like a misconfigured course policy or missing cookie flags.
Yeah.
We could read about tiny pilot vulnerabilities online, but it couldn't actually, click the buttons and navigate the interface to find the RCE.
That's still a major roadblock for these text-based models.
A huge one. And it also led to some classic false positives, even with a Triager.
Like the one with the login page.
That's a perfect example. Artemis reported that it had successfully logged into a service because it got a 200 OK HTTP response.
Which usually means success.
But what it missed was the context. That 200 OK was actually a redirect straight back to the login page. A human in a browser would see the page reload and instantly know they'd failed. The agent just saw the status code and thought it was in.
Okay, but here's where it gets really counterintuitive. That very weakness, its reliance on the command line, actually became a tactical advantage in one specific case.
This is my favorite story from the paper. It's the tale of two IDS servers.
Go on.
So 60% of the human testers found a vulnerability on a modern Dell IDS server. No problem.
But then they ran into an older one.
An older one, yeah. And this old server was using a really outdated HTTPS cipher suite. So when the human testers tried to open it in their modern secure browser...
The browser just said, nope.
Exactly. Connection refused for security reasons. And so the humans hitting that wall just moves on. They gave up on that target.
But Artemis didn't use a browser.
Artemis doesn't have a browser. It used the command line tool curl with the back flag, which basically tells it to ignore SSL certificate errors.
Yeah.
It sealed right past the roadblock that stopped the humans and exploited the server.
So the thing that made it fail on the modern GUI
Was the exact thing that allowed it to succeed on the difficult legacy infrastructure. It's a fascinating trade-off.
It shows how it can find things humans might miss, not just through speed, but through a completely different approach.
And that brings us all the way back to the cost analysis, because this level of capability is shockingly cheap.
The A1 agent, which still beat half the humans, was $18.21 an hour. Annualized, that's what, about $38,000?
Roughly, yeah. And even the top-tier A2 agent, the one that came in second place, was $59 an hour. That's about $122,000 annually.
The paper puts the average U.S. penetration tester salary at around $125,000.
So even the high-end agent is cost-competitive with a human expert. And it can run 24/7 without getting tired or needing a coffee break. The economics are fundamentally changing.
This democratizes access to high-end security testing in a way we've never seen before.
It really does.
So, pulling it all together, what's the final verdict here? The main conclusion seems pretty clear. Artemis proves AI agents can do sophisticated, real-world penetration testing.
And it establishes a baseline, a foundation for how we should be evaluating these systems going forward. And to help with that, the team is open sourcing the whole Artemis framework.
Which raises the dual use question, right? You're putting a powerful offensive tool out there.
You are. And the authors address that. They argued that transparency is the best policy. We need to have clear empirical evidence of what AI can do so we can make informed decisions. And giving these tools to defenders is the best way to level the playing field.
Now, they did point out a few limitations to this study that are worth mentioning.
Of course, the main one was time. The test was capped at 10 active hours. A real pen test can go on for 1 or 2 weeks.
And the defensive conditions weren't quite real.
Right. The university's IT team knew the test was happening. In a real scenario, a fully tuned SIEM or other defensive system would probably have detected and blocked some of these actions immediately.
So for our listeners, that leaves us with a pretty provocative thought to chew on. Given what Artemis could do in just 10 hours with its speed, its parallelism, what happens when these agents are let loose for the 1 to 2 weeks of a typical engagement?
Right.
How quickly do our defensive AI systems have to evolve to counter an autonomous attacker that's running continuously, trying thousands of parallel approaches, 247? What does that mean for how we build and integrate our security tools? The race just shifted into a much, much higher gear.